Recording. Oh, please remind me the day when I forget to record. Someone speak up, or I'll be full of regret. So yesterday we pretty much finished 1.1 finally. So let's move on to 1.2, which is examples of functions that you probably have seen. I'm pretty sure that we're in the Alex test. So this is just a refresher to remind you that these functions exist. Basically, the first example is linear functions. Linear because they're graphs. It's like a straight line. So what's a linear function? Linear function is a function that looks like this. It looks like all you do is multiply by numbers and add constants. If you so these two numbers have a pretty clear meaning. This is the y-intercept. Also, I mean, there's more ways to write this equation, but I'm not gonna spend time now writing them all. This is the slope. The slope is how for every step you go right, how many do you go up? Or if you're going down, then m is going to be negative. So, for example, f of x equals negative 2x plus 3. This is a function whose graph looks like, well, I just said the number that appears by itself, the constant, is y-intercept, so it goes through this point, and then every time I go one to the right, the slope is negative 2, meaning if I go one step to the right, I go 2 steps down. So this is the line I'm talking about. Or, you know, if you want to put a line, just find 2 points on it by taking your two x values and plugging them in, and then draw the straight line between them. I can make a fancy graph. I want to show you this because it's just so easy to use. You write f of x equals x plus b. Without doing anything, it tells you if you want to make a slider for these letters that you wrote. So now this is the function x plus 1. And I can change the slope, and I can see how the function changes. As I make the slope big, it becomes probably you're seeing it like this. Starts sloping higher to it starts going up as you go to the right until it gets almost vertical. If you make it negative, it starts sloping down. If you make it close to 0, it becomes horizontal. And then as you change the y-intercept, well, the line, just the same line moves up and down. So fun. That's it. Do you have any questions about lines? All right. So the next simplest example is polynomials. Polynomials are what you get from adding, subtracting, and multiplication, not division. So if you take x's and you start multiplying by things, you can get power. You multiply x by x, you get a power of x. You multiply it by a number, you get a number times the power of x, and then you can add and subtract those things together. So polynomials look like this for some. So there's some number here. So all these a's, these are some constants. And then n is a natural number. So this is the powers go from 0 to n. So for example, a polynomial, so here's a polynomial. F of x equals a number times the power of x, another number times another power of x, another number times another power of x, and then I'm bored and then I stop, and that's a polynomial. And well, so the biggest power that shows up is the degree. As the degree gets bigger, your life gets more complicated. For example, if the degree is 1, then it's just a linear function. If the degree is 2, you probably remember it's a parabola, and the numbers that show up, constants, which are called the coefficients, they have they have some meaning, but it gets more and more confusing as your life, as the degree goes up. So what does the plus the dot mean? So yeah, great question. When I write plus dot 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 plus, that means I have no idea how many. I don't know how many things are in this sum. There could be 3, like there were below. There could be 17. There could be 1. So what I'm saying is any sum of things like this is a polynomial, and doesn't matter how many things there are, and since I don't know how many things there's going to be, it's going to be different for any polynomial. I don't tell you it's a sum of 5 things. I just write dots, and then I'm not committing to any number of terms in the sum. For example, I think you would know what I mean if I write 1 plus 2 plus 3 plus dot 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 20. What does that mean? It means I got lazy and I didn't want to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I don't remember. So the dots mean I'm skipping something. And hopefully, normally when people write dots, it's understood that you know what goes in between. Thank you. All right. Maybe instead of this example, I should write a polynomial like this. For example, if you go a4 x to the fourth plus a3 x to the 3 plus a2 x squared plus a1 x plus a0. So here, this n that I wrote is 4. So the sum goes from 0 to 4. Okay, so polynomials get more and more complicated as the degree gets bigger, but we can still sort of understand. So how about I go like this? So here's a degree 2 polynomial, a parabola, and well, right now I'm not gonna do much with this, but maybe you can try this later and see for yourself, because I think I find this pretty useful. Like, playing with these things really gives you a sense of, for example, what A is doing here. I can see that as A gets bigger, the parabola gets skinnier, and it goes up. If I make A negative, the parabola goes down, and it gets also skinnier. If I make it smaller, either a positive small number or a negative small number, the parabola gets thicker, I guess, which also has the same effect as zooming in. C is still the y-intercept, so changing it doesn't change the shape, it just moves it up and down. And B, it's more confusing what it does, because it moves the parabola, also doesn't change the shape, but it moves it in this way that doesn't change the y-intercept. No, you give it a try. Maybe you can write the equation differently. For example, if we write, so this is going to be basically the same thing, the letters. If you remember at some point in your life completing a square, if I go like this, then B moves the parabola horizontally, and C moves it vertically, and A changes the shape. You try this. I'm gonna put this link in the notes so you can see it later. Or you write your own. Okay. So that's polynomials. So what's next? I think rational functions. What's the subscript of the A does what again? I'm confused. Right. So that's a good question. So what does it do? The thing is, what I wrote here, for example, means exactly the same thing as, I mean, if the letters are the same, if the letters represent the same numbers, this is the same as giving it 5 different letters. The thing is, at some point I'm going to run out of alphabet. Like, if I don't know what the sum looks like, am I breaking things? I could write AXN plus bxm minus 1 plus cxm minus 2. But then I'm sort of going alphabetically. I mean, I could write z, but that means I'm not saying necessarily there's 26 things. So since I don't want to run it off alphabet, it's just gets confusing. When you have a bunch of letters, sometimes it's better to just say, call this one instead, call this one an, give them a number each one, give it each one a number. So here I could go if I write A3, this is so smart that it understands that I want a subscript. So what does this mean? If I write this, the computer understands that what I want is to see 4 different letters. So this is exactly the same as if I had called these A, B, C, and D, but at some point writing numbers it just gets less complicated. So just try writing this polynomial and flying these things around, see what you see. Does that make sense?
Yeah, so you're basically saying like the subscripts are just like placeholders when you don't have like actual numbers that you're using, so you don't get confused how many like.
Yeah, I mean, I want to make it clear that the A3 and A4 could be different, or they have nothing to do with each other, right? So if I call them all A, it's gonna be confusing. That would be terrible. So just instead of going A, B, C, D, I'm going A1, A2, A3, and it's just a name that I'm giving them. It's like if I was fed up with calling you by your names and I called you instead of Aaron, Alex, Brendan, Cole, I would go student 1, student 3, student 4. That's a good analogy, I think. If I started calling you all by numbers, if I said, all right, 16. I mean, letters don't have feelings, so it's okay in this case. Any more questions? Okay, so now, look, the book says power functions. Yes, I mean, this is not no sort of classification. I mean, linear functions are also polynomials, for example. But I guess it's a good reminder. So power functions are, well, things that look like x to the a, I guess, where a is any number. So, well, if no, that's just right. No, what is it missing? Maybe if I exit and come back in, that fixes everything, right? All right, worked. So if no, what's happening? Oh my god, when do I? Wait, let's try it again. Just when I zoom in. It's so paranoid now. So if A is a natural number, by the way, a natural number is the numbers you use to count 1, 2, 3, 4, 3, 0. I don't know. That's controversial for people. If A is a natural number, then this is just a polynomial. Because it's, you know, x squared, x cubed. So this is a sum of things that look like a number times the power of x. This is a sum of one thing is also a sum. 1 times x cubed plus nothing else. So this is a polynomial, so sort of, I already covered it. One thing that's worth knowing about these is that if you do all the even powers look very similar and all the odd powers look very similar. If you do x squared, so x to the fourth, so x to the fourth, I mean, it's not a parabola, but kind of looks like one. It's just the same except sort of flatter here on the bottom, and then gets more vertical a lot faster. If you do x to the sixth, it's the same but more exaggerated. Fourth. So now this one is even more exaggerated. If you do x to the 20, I mean, at some point it's going to kill my computer. If you do x to the 20, it's way, way, way flatter, way, way, way more vertical once it reaches 1. They all go through the point 1, 1. This probably shouldn't be a surprise. Because 1 to the anything is 1. So this is f of 1 for all of these functions. So that's what you see if you get if you do even powers. If you do odd powers, what you see is that x cubed looks like it's sort of like half a parabola. Again, not exactly a parabola. And then on the other side, it's the other half of, I mean, the exact same shape, but it's facing down. If you flip the picture upside down, it looks exactly the same until your computer flips and your screen flips, and then that was pointless. And again, as you take bigger odd powers, they get flatter. It's the exact same thing. They get flatter close to 0, get more vertical close to 1. And then at some point, you just get extremely flat and vertical. Why is this difference? Well, that's because if you take -1 to an even power, or any negative number to an even power, you get +1. So all the even powers are positive functions. But if you take a negative number to an odd power, you get -1, which is showing here. So that's what whole power functions look like. We could put more exponents in there. exponent is the number that goes to the top of a power, remember. Ooh. The number could be a fraction. So if you have a fraction, something. So there were these things in your childhood telling you how to operate with powers. For example, if the exponent is a product, if you take that becomes the power of the power. For example, if you take 2 to the 3 to the second power, that is not proving, I'm just giving you a way to remember this. 2 to the 3 to the second power is taking 3 2's and squaring that, which gives you a total of 6 2's, which is 2 to the 3 times 2. So, and then hopefully you remember that the power of 1 over something is the same thing as taking a root. So when you have fractions in your exponent, that is really some function that has to do with the root. So for example, x to the 1/2. Ooh, it's exciting function. X to the 1/2 is the square root function. It's exactly the same. You can see both exactly the same. This one is a parabola. It's just the same shape as x squared. And well, all the other, if the exponent is bigger than 1, they go up. If it's smaller, they go down. Well, that's not a fraction, so that's just a whole number. Then some of them, one thing that's important, that some of them are only, you only see, you can only define them for positive numbers. So only positive numbers have square roots. So for example, run out of space, to the 1/2, which is a square root function. What it looks like, it's like this, like I just drew, alpha parabola. This function has domain non-negative reals. If I want to take the square root of -1, I can't. So what if A is irrational? I'm gonna leave that for later. I mean, I would hope you remember, but I don't know if I can hope that much. So is there a function x to the pi? Well, there is. It makes sense to take the pi's power of something. For like, look at it here. And how can we understand such a function? Well, one way to understand it is by saying, how many digits of pi do I know? I know 2. I know that pi is bigger than 314, and I know that pi is smaller than 315. So that's going to mean that x to the pi is going to be between x to the 3.14, which is a fraction, right? Because this is the same as 314 divided by 100. And so it's going to be between this one and that one, 315. And I mean, indeed, you can see that they are. I mean, they're so close. They're so close that we can't really see the difference. When we zoom in, we see, yeah, it's in between. So if we wanted to compute x to the pi, we could just try to get closer and closer using rational numbers. For example, if I wanted to be closer, so this is at this point it's already almost 3 decimals, and I could keep going. Honestly, I mean, it's not like you need in this class to know exactly what the real powers are. You just have to believe that they exist. All right. So next on the list, I'm not gonna say much about, are rational functions. Rational functions are what you get. Polynomials were what you got from adding, subtracting, multiplying. Rational functions are what you get from doing those 3 things: adding, subtracting, multiplying, and also dividing. So when you do all those things, you get functions that look like a polynomial divided by another. Where these two are polynomials. Maybe I'd rather write out the polynomial. So I don't know how long this sum is, so I should start with, I'm just going to call them the n something. So I don't know I don't know the degree of this polynomial. I don't know how many things are in this sum. And then the denominator is another polynomial. So I better use different letters. And I don't know that the degree is the same or if it's different. So I'm going to call the degree m. And then this is what a rational function looks like. And at some point in your life, you'll learn that if you add 2 rational functions, for example, you get a rational function because you know how to add fractions. So I don't know what to tell you about what these look like. Because they look in a bunch of different ways. Something like this. So, for example, here's a random rational function. They have these things called asymptotes, which are a whole thing in this course, so I'm not going to say anything more about them right now. I mean, often they do, sometimes they don't. I don't know, they can look all sorts of ways. You write some rational functions here and see what they look like. And finally, there's algebraic. So let me show you an example here. So anything I can think of where you have sums, subtractions, multiplication, and division. So finally, we have this thing. So rational functions, everyone calls them that. Algebraic functions might be something I think Stewart made up. But according to Stewart, the functions, he calls algebraic functions the functions that you get from doing all the stuff above and then add roots, any sort of roots. So these are anything you can get from addition, subtraction, multiplication, division, and roots. So for example, so now I'm just going to write a random formula involving these. X plus the square root of x minus 1 divided by x squared times the cubic root of x. So that's an example of an algebraic function. Okay, are there any questions?
Are we not gonna do like trig function and stuff like that, or just?
Oh yeah, I'm gonna name all the functions. Trig functions are the next thing on the list.
I got you.
So are we not really getting into rational functions? What are irrational functions? There's a thing, I mean, if by rational functions you mean functions that are not rational, I mean, I guess if I'm calling these rational, that means that these ones are not irrational. Also, trig functions, exponentials, logarithms, people call these transcendental functions. It's a more common term. So I know how to spell that. Is there an N in there? Oh, there's an N in here. Pretty sure it's like this. So transcendental functions are what people call every function that is not a rational function, like trig functions. So the thing is, these are like the functions you see in calculus, but in real life, you see all sorts of crazy stuff. Basically, nobody are in, these are just like the best case scenario where the things you're looking for described in terms of these functions. Really, there's no reason why. So, okay. I'm not going to review all of trig, isn't that the whole course, but I'm going to review sine and cosine, which are the most important functions that there are in trigonometry. So sine and cosine. So what is super important to know about sine and cosine? It's important to know which is which. So I feel like if I tell you this, you know how to draw them. with the lowest point at high -1 and the highest at high 1. So they're both waves. I mean, one looks like translation of the other. Sine of 0 is 0, and cosine of 0 is 1. Sine of 0 is 0. Yeah, and it starts by going up. Cosine of 0 is 1, and it starts by going down, which you can remember by drawing the triangles. And they repeat, both repeat every 2 pi. I feel like this is all you need to know to make a good drawing, which, what let's see if I can make a good drawing. So sine. So I just told myself that I have to start at 0, and once I get to 2 pi, I have to do a full wave. So at pi, I'm going to do a half wave. So that's what it looks like. So this is 1, this is -1, and it continues for the negative numbers. And cosine of x, it's pi, it's sine, but translated. So pi, 2 pi, I said it starts at 1, and then it goes down. So here I have to have done half a wave. Oops. And the same on the left-hand side. So if you can make this picture, I think, for example, it's easy to tell just looking at the picture that sine of pi over 2 is 1, because it's just exactly a quarter of the way there. I mean, hopefully you've seen these before. So, which is gonna go now? I want to say. So, what does this mean for the range? Anyone know?
In the range, like the strong bracket or whatever you call it, the square bracket, -1 to 1.
Right. Yeah. Exactly. The range is the closed interval, -1 to 1. So this means all numbers between -1 and 1 including both. So by the way, the range, like I said yesterday, is the values you can have. So can you have an angle whose sine is 1? Here it is. Can you have an angle whose sine is 1/3? Well, it's smaller than 1, so I don't know what the angle is, but it's somewhere in there. Can you have an angle whose sine is 3? No, you can't. because it's bigger than 1. Can you have an angle whose sine is negative 0.8? Oh, yeah. And you have an angle whose cosine is negative 3? You can't. So, I mean, this is not a trig class, but I'm gonna teach you something that somehow not everyone gets taught in trigonometry. So there's these angles which are very useful to know the sine and cosine of. These angles are, I mean, these are the only angles with nice sine and cosine. They're between 0 and 90. They are 30, 45, 60, and 90. 90 is pi over 2, so 45 is half of that. It's pi over 4 radians. Anyway, we should be, I mean, in calculus, when you use sine and cosine, you're always working with radians. I said it repeats every 2 pi, not every 360. 60 is 2/3 of pi over 2. So it's 2 pi over, sorry, pi over 3. Pi over 3. And 30 is half of that, so it's pi over 6. So if I wanted to know the sine of these angles, I mean, this you've been forced to memorize at some point. Here's how to remember it really fast. You write a denominator of 2 plus of 2 everywhere divided by 2. Oh, you're doing it. Oh, it's doing the thing. Oh. So you write a denominator of 2 everywhere. And then two. And then the numerator is in order √0, √1, √2, √3, √4. Of course, √4 over 2 is 1, √0 over 2 is 0. And the cosine is the same sequence in the opposite order. 4, 3, 2, course √1 is 1, 1, and 0. And there you go. Now you know the sines and the cosines of all the important angles. The unit circle helps if you don't remember a trig. I mean, that's true as well. All right, so I guess the third favorite trig function is the tangent, which is sine over cosine. And then there's 1 over sine, 1 over cosine, 1 over tangent. They all have names. And then finally, to end this class on a super high point, what's the most important trig identity? There's only one correct answer to this question. I'm asking you. I mean, am I asking you to read my mind to see which one I think is the most important? A little bit, but also the answer to this one is indisputable. So 1 second, and you guys, no one remembers any trig identity? All right, Matthew got it right, Mr. Irwin. Sine squared plus cosine squared is 1. That is the most important thing in your life, absolute mood. And with that mood, we're done for the day. You can go get your bagels.